all of us designing big SoCs use emulators to verify them. And for my whole career, at least, emulators have always been odd beasts. Weird proprietary shapes and sizes. Some of them sort of look like drones from some sci-fi series, and which is great until you get them in-house and your IT people start trying to put them in standard server spaces. And they freak out because nothing about emulators is standard at all. They end up kind of zip-tied to a utility pole or duct taped to some other computer box. And then, when you want to expand them, it seems like half the time they're based on some obsolete proprietary standard, so then you have to buy a whole new one for around $1 gazillion. Hi, I'm Amelia Dalton, host of Jock Talk. What most of us really want is an emulation system that looks and works like a normal server. Luckily, my guest today is Frank Shirrmeister of Cadence Design Systems, and Frank is here to tell us about the new Palladium Z1 Datacenter-class emulation system, which, you probably guessed, is powerful, scalable, and is in a normal data center style form factor that won't freak out your IT people. I promise. Before we get started, don't forget to click that link. There you can find out more information about the Palladium Z1 emulation system from Cadence Design Systems. Hi, Frank. Thank you so much for joining me today.
Hi, Amelia. How are you doing? It's great to be here.
So we're here to talk about emulation, and Cadence has been in the emulation business for a really long time, right? Tell me a little bit about the history.
Yeah, it's really 28 years. The first emulator, the RPM, was built based in 87, 88 by QuickTurn, and that was FPGA-based architectures. We later had processor-based architectures coming in 95. QuickTurn got acquired by Cadence, and then Axis, the other acceleration company, came in. And eventually, back in 2010, Palladium XP was born as the combination of both the acceleration and emulation sides. And it's a great time to be in emulation because we now have arrived with our latest invention, with our latest leap here at a data center ready emulation system called Palladium Z1.
Okay, data center ready. That's cool. But tell me exactly what that means.
Sure. So data center ready is really the physical characteristics. It's in a 19-inch rack. It's the same racks you find in data centers, uses the same power. The key piece of making this really an enterprise emulation platform is in the throughput it provides. It's really becoming a compute resource. We started that back in 2010 with Palladium XP, and we now have fully moved it into the data center, providing 5 times greater emulation throughput and very efficient workload allocation. It's also scalable for everybody from small jobs at the IP level to the full SoC level.
Okay, cool.
What the IT folks are always very interested in are things like total cost of ownership. So it's 92% smaller footprint, 44% better power density, and it can be used for a large number of use models so that you get the best out of your system. So that's really making it a data center class emulation system.
That's impressive. So what kind of problems is Z1 addressing?
Of course. So if you look into a modern SoC today, you have lots of IP components for standard IOs, for the infrastructure. You have differentiating IP,
right,
which the user adds. You have many cores, so software is a key issue. You have lots of software in the system as part of the core functionality, so the bare metal software stuff. And you have applications in the system. So the key concern here in all this is to reduce the cost of development and the risk, and it's largely driven by software.
Oh, okay.
And what we see today, when you look at the IBS data here in the growing chip cost, the customer spend today is really largely on the software, so that's a lot of people working on the software. But the EDA tooling, what they actually use in tools for software and EDA, is kind of a mismatch. So there's what we would call an automation gap between what the user is spending his effort driven by software and what the tools are in there. And that's what we're trying to address with it.
So, Frank, it seems like there are a lot of levels of abstraction here. Where does Z1 play? At the IP level or the whole chip? What exactly are we verifying?
Yeah, from an enterprise perspective, you'll find workloads, jobs to be done for verification from small to very large, right? So you have IP blocks in the up to 16 million gate range, I would say, with some software attached to it. You have subsystems these days, taking a full subsystem and you're trying to verify that. And then you have the full chip, of course, with all the software around it connected to the system environment. So you have various job sizes. You have the need to go back and forth between the different levels. If you find a bug in one, you might have to re-trigger verification of some of the components in it.
Okay.
So it's a very complex picture with various workloads which need to be executed in the system.
In EDA, we're hearing a lot about different verification engines these days. What does Cadence think about that, and how does it fit in with the Z1?
Oh, it actually fits perfectly. So Z1 is part of what we call the System Development Suite, which we started rolling out back in 2011. It was really at the time the connection of virtual platform, FPGA-based prototyping, emulation, and simulation, those 4 blocks to the left. Since then, we have been rolling out inventions per year at a very, very large rate. Anything from improving the individual core engines from simulation, emulation, formal high-level synthesis, all the way to FPGA-based prototyping, adding cross-platform aspects like the Indago debug, verification management, verification IP, and adding solutions. And the latest piece in here, the latest upgrade at the core engine level, if you will, is Palladium Z1.
Okay, say I've got my Palladium Z1. What does my typical day look like? What would I actually do with it?
Sure, what a verification engineer and also the hardware software verification guys, what they are doing, they are really going through this, what we call the verification productivity loop. The emulation throughput is determined by it. So you build your workload, you have something to verify. So you compile it, which is determined by compiler speed. You may need multiple workstations for it. Then you want to allocate as many workloads as possible in parallel. So you have a verification team creating hundreds, thousands of workloads of jobs, verification jobs, hardware and software to be executed, all different size, as we said earlier, from IP to SoC, and different lengths. It may be from an IP verification to booting an OS in a different context for the full SoC. So it's all about how efficient can you utilize your compute resource, in this case the emulator. Then you run the workload, so that's where it's all about the speed, how fast does a machine execute. And then you find issues. Nobody's perfect, and verification exists because there are bugs in the system. So here it's all about how deep are my trace buffers, how efficiently can I trigger and look at software traces and so forth. So this loop of build, allocate, run, debug goes on and on and on. And if you look into a project, this is like done thousands of times. People are telling us at this point they're running billions, trillions of cycles to verify these systems, sometimes billions of cycles per week. So it's a day-to-day life, and it's a never-ending loop, so to speak.
Frank, that diagram is kind of scary. That's a lot of times through the debug iteration loop. It seems like throughput will be really important. Tell me about how the throughput has improved.
So Z1, since Palladium XP back in 2010, we have been really focusing on improving the whole throughput aspects of getting through this loop as fast as possible. So what Z1 has improved on, it's twice as fast compared to Palladium XP. With respect to compile, we go up to 140 million gates per hour on a single workstation. Allocation is much more efficient than Palladium XP, which was already a leader in that space.
Okay.
So we'll talk a little bit more about that, how you can efficiently reshape your workloads in the system.
Great.
Speed has improved. We see an average up to 50% improvements, and debug has improved as well with deeper trace buffers, more capabilities to trigger dynamically, and also being able to look at software traces and so forth. So the overall throughput has greatly improved, and it's really very, very competitive, as you see from the numbers compared to the competition here.
Wow, that's a pretty dramatic change. How does Palladium Z1 achieve those improvements?
So really 4 pieces to look at. There's the engineering productivity, scalability, virtualization, and then the cost of ownership. So on an engineering productivity side, we see about 5 times greater emulation throughput going through this loop, and this is really measured across a variety of workloads and assuming a regression suite of lots of tasks.
Okay.
It's about an average 2.5 times more efficient in mapping workloads into the emulator than its competitors in the market. It's very efficient in packing the tasks into the system. Twice as fast compilation speed, up to 50% higher average performance. Then on a scalability perspective, it scales from very small block-based verifications in the 4 million gate range all the way up to multi-billion gate verification. So in a single rack, you get up to 576 million gates.
Wow.
And it all scales up to 9.2 billion gates with up to 2,300 parallel jobs. So it can be set up in an existing data center, is scalable there. And we have done a lot of really stuff. We could geek out a lot about things like redundancy. You can pull out blades from the system
Cool.
as it runs, and there's redundancy, and it has really data center reliability and availability. And because we are in a data center, it's all about virtualization. So you can virtually reconnect the targets, meaning the items the chip talks to, with a backplane. We'll talk about that in more detail. So that's virtualized. The jobs can be reshaped and efficiently packed. That's kind of like playing Tetris, as we'll see. We have pre-packaged the interfaces, and you can work with offline databases, something we call the virtual verification machine.
Cool.
And then because it's data centers, it's all about the cost of ownership.
Right.
We have 8 times higher gate density, 92% smaller footprint, and 44% better power density than our previous system. So it's a huge leap forward to make the Palladium series with Z1 data center ready.
Wow, these things can be huge. Now, you mentioned a lot of workloads, and one thing that seems like a big challenge is that so many people needing to do so many different verification and debug tasks at once. How do you allocate the machine resources to keep people from stepping on each other's toes?
Well, for that we invented what we call advanced job placement, and each of the blocks in this diagram here has about, it's called a domain, has a 4 million gate. If you compile a design, in this case for about 20 million gates, it can be reshaped and mapped into the system in different ways. So you can move it around within the system.
Okay.
You can even do things like split it. The domains don't need to be next to each other. So you can reshape and move jobs from one domain set to another while altering its shape. So you can imagine if you have lots of different workload sizes, you don't want to be in a situation where now a very big job, let's say 200 million gate comes in, which would need about 50 domains. Well, you want to reshape this in a way, you want to use the shapes so efficiently that you can reallocate those within the system. So that's what we meant by workload efficiency being greatly improved compared to other systems. So you are not having to wait to starve out the system. If a big job comes in, you simply reshape and remap those tasks without having to recompile.
Ah, okay. Now I see why you said it was like Tetris. So with our current emulators, we end up having to move hardware around a lot. But with this system, how do you manage all that cable switching in this allocation process?
So we have also virtualized the external connection. So there was always a concern about things being connected, things like USB, PCI Express, Ethernet, and so forth being connected directly to the box. Given that we are in a data center environment, we also have virtualized the access.
Okay.
So we have what we call target pods, which can be placed up to 30 meters away. and you have a logical crossbar on the system, and you can connect up to 24 target ports and connect them to any job in the system. So there's really no recabling necessary at all. You can switch virtually between targets and jobs.
A lot of teams are spread out all over the world, and it sounds like there could be a lot of setup required. What about users that want to access the emulator remotely?
So there are two things here. So we have a couple of cool inventions here. One is the Emulation Development Kit, which is a pre-configured solution for providing you the accuracy and remote access while maintaining high performance. So we have combined the connections and the software running on a host for things like PCI Express and so forth to allow external access and have it pre-configured. So it's kind of like when you get the Star Wars Falcon at Christmas, you get it pre-configured. You don't have to build it on Christmas evening. Software is all pre-installed. It works together and it's remote accessible.
Nice.
That's one. And the other one is what we call the virtual verification machine. So when you have a run and you create a database, and this is like gigabytes of data being created here, we have the ability to now allow offline access in a much more elegant fashion, and what we call the virtual verification machine, where you can literally have tens and hundreds of users giving them access for interactive debugging on that database, so you don't need to rerun and block the machine. There's really virtualization, if you will, here at 4 levels, from the job to the connections being pre-configured and then allowing virtual offline access.
Okay, I've got it. Now, you've been mentioning use models a lot. Tell me more about what those are and how they work.
Yeah, Palladium has been a leader already with use model versatility quite a bit. What you see here is a set of categories from the core emulation, where you have multi-user regressions, the standard in-circuit emulation through acceleration, where you can merge the coverage from incisive enterprise simulation runs with Palladium runs. You can accelerate gate level simulations, hot swap even between incisive and the emulator. And then you have categories like hardware software, bring up software debug, verification of scenarios, optimizing for low power with the dynamic power analysis and verification of UPF, CPF, all the way to the architecture analysis and even post-silicon, where people generate vectors. So we count about 22 use models in total. We think there are about 14 major ones, if you will, in very broad adoption.
One of the messages I'm getting is that this data center class idea lends itself well to scaling. Now, tell me about how the system scales when we want to use some of the enormous capacity we've been talking about.
Well, so we had the racks that come in a liquid-to-liquid and air-to-liquid cooling environment. So you have up to 576 million gates per rack. If you put 4 next to each other, you get 2.3 billion gates. And for 16, you get to the 9.2 billion gates. So that's a lot of verification capacity as a compute resource in the data center.
For sure.
And that fits really people from small who may start with a not fully filled rack at 192 million gates, all the way up to really any verification needs you might have in your company. It's a blade architecture where you can fill in and with all the redundancy, plug out, even hot plugged new blades in there without disrupting the rest of the system.
Okay.
From a scale perspective, the Palladium series in itself, I had kind of given an overview of the history earlier, but if I look at just the Palladium generation since 2001, it's amazing how we are now at 17% of the original power density. We have increased the capacity density per chassis from 8 million gates to 576 million gates, and the max capacity from 128 to 9.2 billion gates. So it's amazing. And with the integration into the verification flow and the virtualization capabilities, which we have been introducing in the XP series and now rolling out in Z1, Z1 is really data center ready with what we are announcing and what we're rolling out here in the fall of 2015.
Okay, that's impressive and a lot to absorb. Can you go over the high points of the Palladium Z1 again for us just one more time?
Sure. So the summary is really emulation has arrived in the data center. We have an enterprise emulation platform. It's all about the emulation throughput, where we are up to 5 times greater than the closest competition here. It's all about how efficient the workloads can be mapped into the system. So we are on average about 2.5 times greater there. It scales, so scalability is important from IP blocks to full systems on chip. So you can scale the capacity up to 9.2 billion gates with more than 2,000 users, 2,304. It's the best total cost of ownership you can get. 92% smaller footprint, 44% better power density compared to Palladium XP. And we have these use models we talked about. So it's not a one-trick pony. You can do anything from pre-silicon, post-silicon, low power activities, acceleration, in-circuit emulation, and use the extensive virtualization capabilities. So it's really ushering in a new era of data center class emulation here.
Fantastic. Well, I think that's all I have time for today. Thank you so much for joining me once again, Frank.
Thank you. It was my pleasure.
You didn't forget to click that link, did you? There you can find out even more information about the Palladium Z1 emulation system from Cadence Design Systems. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out EE Journal's YouTube channel or the on-demand section of eejournal.com.